In the last video, we saw the definition of matrix multiplication, and we saw how to compute examples in practice. So just to remind you, if you had two matrices A and B, and it was legitimate to multiply those two things together, so if the number of columns in A was the same as the number of rows in B, then you could find their product by saying that their product was the matrix whose ij entry was obtained by multiplying together the corresponding entries in the ith row of A and the jth column of B and adding up the results. In this video, we're going to look at matrix multiplication in a slightly different way, which gives us useful insights into how it actually works and will pay off later when we're trying to prove interesting things about matrix multiplication. And we're going to think about matrix multiplication column-wise, so one column at a time. So we'll focus to begin with. I want to do an example where we multiply a matrix into a single column vector. So here we have a 2 by 3 matrix, and we have a 3 by 1 column vector. So I can multiply those together and the result will be 2 by 1. And in fact, when you do this, to get the 1, 1 entry, you multiply the first row of the first matrix by the first column of the second matrix. So you get AX plus BY plus CZ. And for the other entry, you'll get DX plus EY plus FZ. That's multiplying the second row by the first column. So let's think about this a little bit more, because we can actually separate this into bits. So if you imagine taking the X's and the Y's and the Z's out, and thinking of this as a sum of three 2 by 1 vectors, you can see this is the same as x times AD plus y times BE plus z times CF. But what are these things AD and BE and CF? Well, if we just join up what's going on here, well, AD is the first column of the matrix on the left, and BE was the second column, and CF was the third column. So we can write this matrix product as actually a sum of multiples of the columns of the matrix that we started with, so the matrix on the left with the multiplication. And in fact, you can prove really easily using the definition that in general, when you have a m by n matrix A and you multiply that into an n by 1 column vector X, and if you call the entries in that column vector x1, x2, x3 up to xn, and if you let the columns of A being c1 and c2 up to cn, then the matrix product A times x is just obtained by adding up scalar multiples of the columns of A. So you take x1 times the first column of A and x2 times the second column of A and so on, and you add them all up. That is an equivalent expression for the matrix product A times x. So this is a really useful thing to have. It tells us something about when we multiply a matrix into a column vector. It tells us the result is obtained by taking the columns of our matrix A and multiplying them by the entries of the column vector and adding them all up. And there's a special name for this kind of expression here. So this is called a linear combination of the columns of A. So in general, whenever you've got a collection of column vectors of the same size, or row vectors of the same size, or matrices of the same size, or whatever, and you multiply those things by scalars and then add up the results, that's called a linear combination of your vectors or your matrices. And here what we've shown then is that when you multiply a matrix into a column vector, so when you form this thing AX like we've just done here, the result is a linear combination of the columns of the matrix A. And that's precisely what happened in our example at the top. You found that when you multiplied our matrix into that height 3 column vector, what you got was a linear combination of the columns of the matrix that was on the left. So we're going to look now just at a really special case of doing a matrix multiplied into a column vector. So what would happen if that column vector just had zeros in it everywhere except for a single 1 somewhere? Well, in this sum here, then what would happen is that all of the xk's will be 0 except for 1. So when you did that matrix multiplication, where you were multiplying into a column vector which just had a 1 in some position and zeros everywhere else, well, all those xk's will be 0, so you might as well just ignore that term, and there would just be a single 1 somewhere. So if it was, say, the ith element of the column vector, which was 1, then what you get is just Ci, the ith column of your matrix. And this is occasionally a useful result. We have a standard name for these column vectors which have a 1 in one position and zeros everywhere else. Those things are called standard basis vectors. And we also have some standard notation for them. So if you have it fix the height n, then the standard basis vectors e1 up to en are the vectors which have a 1 in, well, e1 would have a 1 in position 1 and zeros everywhere else. So this one here would be e1. e2 would have a 1 in position 2 and zeros everywhere else, and so on. So down to this one, which will be en. So that's the definition of these standard basis vectors. So for example, if n is equal to 3, there will be 3 standard basis vectors. e1 will be 1, 0, 0. e2 would be 0, 1, 0. And e3 would be 0, 0, 1. And what our formula from the last slide tells us is that if you multiply a m by n matrix A into the jth standard basis vector, then the result would just be the jth column of A. Because if you go back to our sum at the top here, then all of the x's will be 0 except for the jth, which will be 1. So you just get the jth column of A. So it's sometimes helpful to remember that when you multiply a matrix into one of these standard basis vectors, then it's really simple to get the answer, because the answer, if you multiply into the jth standard basis vector, is simply the jth column of A. So you might like to try that out. I mean, if you want to try an example, why don't you take A, B, C, D and do the matrix multiplication into the second standard basis vector of height 2. So if you check, then what I'm claiming is that you should get here the second column. So in fact, if you do this, you'll see that you really do get the second column of A. Okay, let's see what else we can say about doing matrix multiplication column-wise. So we're going to think about a slightly larger version of the example we looked at before. This time we're going to multiply a 2 by 3 matrix into a 3 by 2 matrix. So the result will be a 2 by 2 matrix. But let's now think what goes on when we want to work out this thing one column at a time. So we're just going to focus on how we would work out the first column of the answer. So let me highlight the first column. Here it is. This stuff here is making up the first column of our answer. So you remember the definition of matrix multiplication and the way we actually work things out. In order to work out things in the first column of our matrix product, we multiplied the rows of the first matrix. So let's give these names. Let's call this A and let's call this B. So to work out the first column of the answer, we multiplied the rows of A by the first column of B. So all this stuff in the first column of the answer just comes from looking at what happens in the first column of B. And similarly, when we want to work out the second column of the answer, so this stuff here, that would come from multiplying A into the second column of B. So the first column of the answer comes from multiplying into the first column of B, and the second column of the answer comes from multiplying A into the second column of B. That's what it means to say that matrix multiplication happens column-wise. So we could express what we've got here as being the first column is A times D1, where D is D1 is the first column of B. So let's just label this. This first column here is going to be D1, and this second column there is going to be D2. And what we've got there is just AD1 and AD2. So a matrix times a column vector, the first column of B, and then a matrix times a different column vector, the second column of B. So in general, what this argument shows is that if you multiply an m by n matrix A into an n by p matrix B, and if you call the columns of B D1, D2, D3 up to dp, then A times B is the matrix whose first column is obtained by multiplying A into the first column of B, and whose second column is obtained by multiplying the A into the second column of B, and so on. And then the last column will be obtained by multiplying A into the last column of B. So let's just see this in action. You've seen an example at the top there where you can see that the first column of the answer was obtained by multiplying A into XYZ, the first column of B, and the second column was obtained by multiplying A into the second column of B, UVW. Let's try another example. So we'll take A to be 1, 2, 3, 4, and we'll take B to be 5, 6, 7, 8, like this. So B has two columns. First column D1 will be 5, 7. The second column D2 will be 6, 8. And when we work this out, well, what do we have? We should, in order to get the first column, that's going to be equal to A times D1, which is 1, 2, 3, 4 times 5, 7, which is 5 plus 14 is 19, and 15 plus 28 is 43. Don't trust my arithmetic, check that yourself. But anyway, that should be giving us the first column. So what we should find is that the first column of the product will be 19 and 43. So the first column of the product was obtained by multiplying the left-hand matrix, so the A here, into the first column of B, which was 5, 7. And similarly, you can get the second column as well. So we would have, 1 times 6 plus 2 times 8. These ones are too difficult for me, but you can work it out, and it will be the same as multiplying A into the column vector 6, 8, the second column of B. So why is this interesting? Well, one reason is that we know what happens when you multiply a matrix A into a column vector. So we've seen that when you do A times X, then the result is a linear combination of the columns of A. We saw that this was equal to the sum from I equals 1 to n of xi, so little xi is the ith entry of x, times ci, where ci was the ith column of A. So every column of A times B is then going to be a linear combination of the columns of A. So remember, a linear combination just means an expression like this.